This is a tutorial to study the one-dimensional cellular automaton using Wolfram's rule number 126. Now, a one-dimensional cellular automaton has a number of cells in a one-dimensional line that can influence each other through inputs. So for one particular cell of interest, let's say this one, it has its particular state, Q, and it also has an input x, L, based on the state of the cell to its left, and an input x, R, based on the state of the cell to its right. So if this were cell Qi, this would be Qi minus 1, Qi plus 1. So rule number 126 can be defined in the following transition matrix. So based on a particular value for the left input and a particular value for the right input and a particular cell value Q, it defines the next state for that particular cell, which we've also been describing using the delta notation, delta of Q and X. So as I just mentioned, rule number 126 defines a rule for how to transition between these different combinations of inputs and state values. And in this case, because there are two possibilities for the left input, two possibilities for the current state, two possibilities for the right input, there's a total of 8 possible combinations. So 0, 0, 0, 0, 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 1, 1, 0, and 1, 1, 1. Right? So these are the 8 possible situations that we might encounter. And rule number 126 defines this column of the transition table. It states that the next state is 0 if the left and right neighbors and the current state is 0, and it's 0 if the left and right neighbors are 1 and the current state is 1. And in all other cases, the next state should turn to 1. Right? So let's see this transition in action. So at time t equals 0, we could have a particular set of cell values. And just to make things, rather than leaving all these spaces between the cells, I'll just put them right next to each other to save a little bit of space. Right? So let's say at t0, the value of this is q0, q1, q2, q3, q4, q5, and q6. Say the value of most of them is 0 except for q3, which we'll say at the initial state is 1. So at time 1, we can then transition these values. So based on the rules, and in this case we'll keep the boundary ones as 0, just because we haven't defined how to handle a situation if there is no neighbor to the left or right. So if the cell value and its two neighbors are 0, it stays 0. Otherwise, if the cell value is 0 and one of its neighbors is 1, it turns to 1. The cell value itself is 1, but its two neighbors are 0, it stays at 1. If it's 0 but one of its neighbors is 1, it turns to 1. And if it's 0 and its two neighbors are 0, it stays 0. So this is how this cellular automaton transitions to time 1. We can follow the same process to advance to time 2. So following the same rules for these 7 cells. The two boundaries we can just keep at 0 as boundary conditions. This one of its two neighbors was 1, so it turns to 1. one of its neighbors and itself was 1, so this one stays at 1. This cell, for example, Q3, changes back to 0 because it's 1 and its two neighbors are 1, so it falls under this last rule, under rule number 126. And these other two turn to 1 for the same reasons as these first couple. So if we advance one more step to time 3, we can follow again the same set of rules. So we'll keep the boundary elements at 0. This stays at 1, this stays at 1, this switches to 1, this stays at 1, and this stays at 1. So similar to the exercise that we saw in class, we do, over time, we get this pattern, which are similar to Sierpinski triangles. And if you have a large enough one-dimensional cellular automaton, you will generate, this pattern will continue out like that. Now, this particular pattern is only subject for rule number 126. There's 255 other rules that generate different patterns, and I'd urge you to take a look at some of those examples online.